Okay, so the plan for today is just to finish up our discussion of series, finish up chapter 11, kind of the main topic, the last main topic of the course that's really related to what I would still call Calc 2. And then in Monday's class, we'll discuss a little bit of chapter 12. I also posted a couple of supplements on chapter 12 as well, and just kind of generally do a course wrap up. The final exam is available. The sample exam, or sorry, the final exam will be available on Friday. The sample exam is available. So you can check out the sample exam on WebAssign to see kind of what the material will be like on the final exam, what the length will be like, how many questions, all of that. It'll be the same setup as the midterm exam. You can use a formula sheet. You can use like the series testing flow chart on the front side and write notes on the back, or you can write notes on the front and back of a piece of paper. However you want to do it is fine. So that's the week of Friday the 2nd through Friday the 9th. I do strongly recommend taking or planning to take the exam maybe Wednesday night at the latest. And that way, if anything does happen, if there is a tech issue or like a power outage, like we've kind of seen last night and today can cause some problems. Then that gives you some buffer to kind of work around that stuff, to reach out to me to get any tech issues sorted out. There are no due date extensions on exams, especially for the final exam, because there's such a tight turnaround between the end of the exam and me having to get grades in so that folks can get all their graduation stuff in order and all of that. Um, so yeah, I think that is all that I have to say about the final exam. And the quote of the day or idea of the day is, don't underestimate the impact of survivor bias. So particularly when you're looking uh, to go into a field, maybe it's a career field or just a field of interest, and you find somebody who's quite successful in that field, the tendency of people, sorry, my allergies have just been uh, really going haywire this morning. Um, so there's a tendency for folks to look at somebody who has succeeded and is at the top of that field and basically just try to follow their path exactly. So, somebody getting into fitness might look at Arnold Schwarzenegger and say, oh, he's published a lot of his stuff about how he worked out. Maybe I'll just work out like Arnold Schwarzenegger did. Or Robert Kiyosaki, the author of the book Rich Dad Poor Dad, he's in real estate. Um, Maybe you look at him and just say, okay, I'll just follow his strategy, and he was very successful, so I might be too if I follow that strategy. But the problem is that you're not Arnold, and you're not as fortunate probably or as lucky as Robert Kiyosaki. So if you try to do Arnold's workout program, chances are pretty good you'll just burn out and destroy your joints or get injured and not making very much progress at all. Or if you try Robert Kiyosaki's financial strategy, which is basically take out a whole bunch of loans, buy a whole bunch of properties, make it really risky, and use that basically fear of going bankrupt to spur you on into finding a way to not go bankrupt. Yeah, if that works out, if you can pull it off, that's great. But you know, I think most people uh, would not be so lucky as to both not go bankrupt and not have a mental health crisis with all of that stress. So, um, these are the survivors of these really extreme approaches, but we have to realize that the end result is of whatever approach is often dependent on three things. Something like uncontrollable systematic effects, things like maybe genetics. You probably don't have, or I don't have, Arnold's genetics. Controllable systematic effects, which is things that are under our control, things like going to the gym and so on. And then chance or luck. Do you just happen to get unlucky one day and tear a muscle or get a bad injury or something like that, and that means you're out of the gym for 6 weeks. So there's some of each of those, and the large outliers, the people who are the ones who write the books and who people look up to most often, are kind of, as Charlie Munger might say, they tend to be a confluence of many tendencies, only some of which we can control. So um, don't underestimate the impact of survivor bias, especially when you're looking at people at the top of their field. Maybe look at them as inspiration, not aspiration. Don't try to be them, but say, that's really cool that a person can do that. Let me try to work to the top of my potential, realizing that, you know, their path isn't going to look like my path and my results might not look like their results. Okay, so continuing on with 11.10, which it always irks me to say that it's in a math book that it's 11.10 comes after 11.9, but it is what it is. So Taylor and Maclaurin series. So just recall the definitions of Taylor and Maclaurin series. These are essentially formulaic approaches to make a power series representation for a somewhat arbitrary function. I mean, it has to be a nice enough function that we can differentiate it as many times as we need to, and that the series converges. But for, lots and lots of functions, we can just kind of plug the function into the machine, turn the crank, and we get a power series representation out the other side. And this is about where we stopped last time. So let's look at some common Maclaurin series. So the first we'll look at is the binomial series. And if we have 1 plus x to the k power, we can start by thinking of k being a positive integer, so 1 plus x to the first or second or third. Well, we could write this out as using the binomial expansion as something like 1 plus kx and so on. So if k is a positive integer, this series actually terminates after a while. However, we can actually generalize this to just real values of k, to either negative integer powers of powers k, or even real numbers, rational numbers or even irrational numbers. So for instance, 1 over 1 plus x, where k is -1, this is 1 plus x to the -1, we can see pretty clearly it's going to be 1 minus x plus x squared minus x cubed and so on. We can see the relationship to a geometric series there. Or something like 1 over root 1 plus x, which is 1 plus x to the -1/2, looks like 1 minus a half x and so on. Or 1 over root 1 minus x, it's 1 plus negative x to the power -1/2, which is 1 plus a half x, etc. And this actually comes up in special relativity. This is related to the Lorentz transformation. We, of course, are familiar with these next couple. 1 over 1 minus x is some x to the n with a radius of convergence of 1. E to the x we saw last time, we generated this a couple different ways. Some n equals 0 to infinity of x to the n over n factorial. And here we have radius of convergence, the whole real line. We also have formulas for sine and cosine. It's not a bad exercise to at least go through one of these and kind of, turn the crank, so to speak, and see how all of this comes out. But we look at sine x, for example, and we see that sum n equals 0 to infinity of -1 to the n, x to the power 2n plus 1 over 2n plus 1 factorial. And something we might notice about this is the power 2n plus 1 is always odd. So odd powers. And in fact, sine x is an odd function. Sine of negative x is negative sine x. And we talked a little bit about last time about how odd functions, that kind of geometric or algebraic symmetry, relates to power series expansions in that the Maclaurin series consists of only odd powers. And similarly with cosine x, we have even powers, and cosine is an even function. So similar thing here. And we actually see that sine and cosine's power series actually look a little bit like the exponential function's power series, in that it has like x to a power over the power factorial. But we have a couple differences here. One, the sine only has the odd powers and the cosine only has the even powers. And two, we have this kind of -1 to the n out in front. So there are some slight differences, but some similarities between sine x, cos x, and e to the x. And nicely enough, sine x and cos x, their power series also converge on the whole real line. And then we have one that I suppose you could take a look at trying to prove, but log 1 plus x and sum n equals 1 to infinity of -1 to the n minus 1, x to the n over n without a factorial. And here the radius of convergence is 1. That was about the best that we could hope for because the inputs into log have to be strictly positive, and 1 plus a -1 takes us down to 0. So the best we could hope for is a radius of convergence of 1. And that's what we get. Okay, so let's take a look at this example. This is kind of a fun example. We're letting go a little bit of mathematical rigor here because so number one, we're dealing with complex numbers here. We're not going to have to do very much with complex numbers, so don't let that scare you away. But this is an identity that comes up from time to time, and it's a lot of people's like favorite math identity, or at least related to people's favorite math identity. And I think there's some cool consequences that come out of it. But we're going to be playing a little bit fast and loose with a couple of things as we go through here. Um, so we're giving up a little bit of mathematical formalism for the ability to, and that's why I say we're kind of demonstrating Euler's identity. We're not really giving a formal proof. So let's take a look at e to the x. E to the x has power series, sum n equals 0 to infinity, x to the n over n factorial. So then what is e to the I theta? Well, that's going to be sum n equals 0 to infinity of I theta to the n over n factorial. Now, again, like, can I do this with a complex number? Well, we haven't really addressed that. There's some nuance here that we haven't addressed, but the long and short of it is the stuff that we're going to do is okay to do, but we haven't really given any evidence even in favor of that, let alone any kind of formal proof. Okay. So I know that I want this to end up looking like a cosine bit plus a sine bit. And I see kind of nicely enough the sine bit has all of the odd powers and the cosine bit has all of the even powers. This gives me an idea of how to proceed. Now, one thing I need to remember is that I is like square root of -1 more or less. I squared then is -1. I cubed is I squared times I, or negative I. I to the fourth is 1, and then I to the fifth is I again. And then I to the sixth is I squared, and so on. So the powers of I have this kind of cyclic nature. So I to the fourth, I to the eighth, I to the 12th, I to the 16th, those are all going to be 1. Or I squared, I to the 6th, I to the 10th, I to the 14th, they're all going to be -1, for instance. Okay, so let me look at, maybe I'll just copy this down instead of rewriting it. Let me look at e to the I theta. And I see the first thing I want to do, if I'm looking to split this into a cosine bit plus a sine bit, first thing I probably want to do is break apart the even parts and the odd parts, the even powers and odd powers. So I'll just note that like this, sum n equals 0 to infinity, but only the evens. I'll kind of make it a little more mathematically precise in just a second. Plus sum n equals 0 to infinity of only the odds, I theta to the n over n factorial. So we're trying to work our way towards something that looks like these summations here. Okay, so if I only am adding up the evens, maybe I'll do these in green. If I'm only adding up the evens, then I have like n equals 0, 2, 4, 6, 8. I could reindex this as something like sum I equals 0 to infinity of I theta to the 2n over 2n factorial. Oh, not n, I switched to I and didn't carry that through to I. Oh, I don't want to use I. I'm using I for the imaginary unit. What should I use? K. So K equals 0 to infinity. I theta to the 2K over 2K factorial. There we go. So what did I have initially? I had like I theta to the 0 over 0 factorial, and then I theta squared over 2 factorial, I theta to the 4th over 4 factorial. That was when n equals 0 to 4. But now whenever k equals 0, 1, 2, I have I theta to the 0 over 0 factorial. When k is 1, I have I theta to the 2 over 2 factorial. When k is 2, I have I theta to the 4 over 4 factorial. So I just re-index things so that I don't have to have this little parenthetical even sitting there at the bottom. And then for the odds, n is like 1, 3, 5, etc. So I'll switch over to k again. Sum k equals 0 to infinity. And when k is 0, I want n to be 1. And when k is 1, I want n to be 3. So I want to jump by 2's starting at 1. So I want an I theta to the 2k plus 1. So here when k is 0, my power is 0 plus 1 is 1, meshing with n equals 1. When k is 1, I have 2 times 1 plus 1 is 3. When k is 2, I have 2 times 2 plus 1 is 5, and so on. So again, just re-indexing, swapping n for 2k plus 1, and then doing the same in the bottom. Okay. So now if I come back to my even powers, I see that I have an I to the 2k times theta to the 2k over 2k factorial. This is the thing that I want to look like cosine. And I do have this like theta to the 2k over 2k factorial bit. This part already matches up. But I kind of think that my cos theta, I should get rid of all of the i's, right? I don't have any i's left over. I don't have any i's floating around in here. I need to get this minus 1 to the n out front instead of i's. Well, I to the 2k is really just I squared to the k power. But what's I squared? That's minus 1. And this sum, negative 1 to the k theta 2k over 2k factorial. That's exactly what I want for cos theta. So the cos theta bit worked out nicely. And then what do I have over here? Well, I have I theta to the 2k plus 1. That's I to the power 2k plus 1 times theta to the 2k plus 1. But I can think of this as I to the 2k times I. So let me pull one of these i's, this one, out front. And then I would end up with I to the 2k theta to the 2k plus 1 over 2k plus 1 factorial. And again, after the I, I'm looking to get a sine theta. So I'm looking for this summation in blue to be sine theta. And I see I almost have it. I have theta to the 2k plus 1 over 2k plus 1 factorial. This bit just needs to become a minus 1 to the n to match up, or minus 1 to the k. And again, I see that I squared to the k is just minus 1 to the k. I squared is just minus 1. I squared is minus 1 to the k power theta to the 2k plus 1 over 2k plus 1 factorial. And that is I sine theta. So we've, I won't say proven, but we've kind of demonstrated Euler's identity. So if we plug in pi, we get e to the I pi equals, well, cos pi is -1 and sine pi is 0, or we get e to the I pi plus 1 equals 0. And this is what some people call like the most beautiful identity in math. It has the exponential number e, the number pi, the imaginary number I, and the arithmetic identity 0 and the multiplicative identity 1, all kind of just wrapped up very nicely in one little formula here. But this formula also has other uses, the more general formula. For instance, we saw in the diff-EQ section, when we had a second order equation and we got a characteristic equation that had complex roots, we used this relationship to figure out what the solution, the bases for the solutions were. So this is a demonstration of that identity. So I think a nice little demonstration. All right, let's find the Maclaurin series representation for this function, f of x equals x over 1 minus x squared. Now here I could figure out f of 0, then f prime of 0, f double prime of 0, and so on. I could go that route, but I can see that I'm going to have to use quotient rule a bunch, and that's going to get pretty messy pretty quickly. Can I find another approach here? So what is f of x? Well, on one hand, it's x over 1 minus x squared. And on the other hand, I want it to be the Maclaurin series. So I'm n equals 0 to infinity of Cn x to the n. Or I have x over 1 minus x squared equals, well, if I expand out that right-hand side, that's like C naught plus C1x plus C2x squared, and so on. Or really what I see is I can multiply both sides by 1 minus x squared. And that right-hand side just turns out to be uh, essentially another series, another infinitely long polynomial. So if I can find all of my CNs, if I can find what is C naught, C1, C2, etc., then I can then I can establish what my power series representation has to be. Well, okay, so what do I know? I mean, on the left, I can think of X as like 0 plus 1x plus 0x squared plus 0x cubed, and so on. That's what just X is. I can think of it that way. And on the right, I can start collecting similar terms. So I could ask, okay, what is my constant term on the right going to be? After a while, everything is going to have at least an X in it from this product. The only way I get a constant term is 1 times C naught. So that's my constant term. What about a linear term? Well, I can get a linear term if I have C naught times negative X. So I have negative C naught. Or I can get a linear term if I have C1x times 1. So that's positive C1x. What about a quadratic term? So what's going to multiply x squared? Well, that's a 1 times C2. That's a minus x times C1x. And a minus x squared times C naught. What about x cubed? Well, to make an x cubed, I could have 1 times, let me write another term out here. So for x cubed, I could have 1 times x cubed with the coefficient of C3, or negative x times C2x squared. So that's a minus C2 coefficient. Or a negative x squared times C1x, that's a minus C1 coefficient. I could go out another one, but I think I see the pattern that x to the n is going to have Cn minus 1 minus Cn minus 2. And now I see that my constant term on the right has to match with the constant term on the left. So C naught must be 0. I see that C1 minus C naught has to be 1, or, well, C is not 0, so C1 has to be 1. And then for everything else, Cn, that's a 0 on the right-hand side, has to be equal to Cn minus 1 plus Cn minus 2. All right, my first C and then minus the other 2 has to give 0, so I can pop those minuses onto the other side as pluses. For what is this? N bigger than or equal to 2. So I see I get 0, 1. C2 would be 1 plus 0 is 1. C3 is C2 plus C1 is 2. C4 is 2 plus 1 or 3. I actually see that Cn is basically like the nth Fibonacci number, right? I go 1, 1, and then each one after that is the sum of the previous two. So it's kind of interesting that I end up with the nth Fibonacci number being my coefficient for the power x to the n for this specific function here. Any questions on this? Okay, let's look at this example. Find the third degree Taylor polynomial for f of x equals x to the 2/3 with center a equals 1. Then use Taylor's inequality to estimate the accuracy on the interval 0.9 to 1.1. So if we're at center a equals 1, we have to find f at 1, f prime at 1, f double prime at 1, and so on. So let's start by finding the derivatives. So f is x to the 2/3. F prime is 2/3 x to the minus 1/3. F double prime of x is negative 2 over 9, 2/3 times negative 1/3, x to the negative 4/3. The third derivative, we bring the negative 4/3 down, we get a plus 8 over 27 x to the negative 7/3. And the fourth derivative, bring a negative 7/3 down, and we get over 81. 7/8 are 56 with a negative 56 over 81, x to the minus 10/3. Okay. I note that f of 1 is 1. F prime of 1 is 2/3. F double prime of 1, negative 2/9. F triple prime of 1 is 8 over 27. And my goal is to find the third degree Taylor polynomial, or the kind of third partial sum of the Taylor series. So this is, if we remember what our Taylor formula is, it's the n equals 0 to n equals 3 terms added together that look like this. The nth derivative at the center over n factorial times x minus center to the n. My n equals 0 term is the 0th derivative, or just f at 1 is 1 over 0 factorial x minus 1 to the 0 power. The n equals 1 term is f prime at 1, the first derivative at 1, 2/3 over 1 factorial x minus center to the first power. The n equals 2 term, the second derivative over 2 factorial x minus 1 squared, and the third derivative 8 over 27 over 3 factorial. This is the n equals 3 term, x minus 1 cubed. Or if we clean this up a little bit, I can give myself a little more room here. X minus 1 to the 0 power is 1. 0 factorial is 1, so I just have 1 here for the first term. 1 factorial is 1, so I have 2/3 x minus 1. And then I have minus 2 over 9, but then divided by 2 factorial, which is just 2, or that's minus 1/9. X minus 1 squared. And then what do I have here? Well, 8 over 27 times 1 over 3 times 2. This 2 divides with one of the 2's in the 8. And the 27 times 3 makes an 81. So I have a plus 4 over 81, x minus 1 cubed. So this would be like my cubic approximation centered at 1 for this function, f of x equals x to the 2/3. So that's an estimate, but an estimate isn't all that valuable if we don't have bounds on the errors. Okay, so let's then look at the remainder. The remainder at absolute value is bounded above by this thing, some number over n plus 1 factorial. Well, n equals 3, so the next factorial is 4 factorial. The thing on top is related to the fourth derivative. Remember, the remainder bound kind of looks like the first thing we leave off, right? The next term down here would have been the fourth derivative over 4 factorial times x minus a to the fourth. But here we have times absolute x minus 1 to the fourth. The numerator, this m here, is the upper bound for the n plus first derivative. So what is my fourth derivative? That is this negative 56 over 81, x to the negative 10/3. Okay, so let me switch colors here on x in 0.9 to 1.1. That was my interval of interest. I'm doing the approximation at the center, a equals 1, and I'm going 0.1 to either side. And my question is, what's my upper bound for my error? My fourth derivative, I notice, is decreasing on this interval. So the max for x in 0.9 to 1.1, the fourth derivative of x, is going to be negative 56 over 81 times 0.9 to the negative 10/3. Not the nicest number in the world, but it is what it is. So this is what is m, which will be over here. And this, I know the biggest this can be is 0.1. The further I get away from 1, the larger this is. And the most that I get away from 1 is 0.1 units away, either the left or the right side. So the upper bound for the error in this approximation is going to be negative 56 over 81 times 4 factorials. 4 times 3 is 12, times 2 is 24. We could probably simplify that fraction, but it's not like we're going to end up with something nice at the end anyway. Times 0.9, the negative 10/3, and then times 0.1 to the fourth. Or you can write that as 10 to the minus 4, I guess, if you wanted to. We might be able to do some simplification here by hand, but I plug this into the calculator and it's approximately 1.18 times 10 to the minus 5. So the error in the approximation, provided I only plug in x's between 0.9 and 1.1, will be bounded above by about 1 times 10 to the minus 5. That's a 5 there. So this is the precise upper bound coming out of Taylor's remainder. And then this number is what that approximately comes out to. Now I might, practically speaking, do better than this, right? This is an upper bound. So maybe at a specific X value between 0.9 and 1.1 that I plug in, I might be more accurate than this, but I'll never be less accurate than this. I'll never be further away than this. Okay, and then let's look at one last example. So we'll take a look at this example. A car is moving with speed 20 meters per second and accelerating at 4 meters per second squared at a given instant. Use a second-degree Taylor polynomial to estimate how far the car moves in the next second. And then kind of a follow-up question, would it be reasonable to use this polynomial to estimate the distance traveled during the next minute or 60 seconds? Okay, so let's think about this. Let's imagine that we have a car here, and let's call this position S. That's what we often use to denote a position, and position at time t. And let's set let's just set S of 0 equals 0. We'll choose that to be our beginning point. The car is moving with an initial speed and it's also accelerating. So it's coming into point 0 with the speed already and kind of on the gas. And we want to know, well, approximately, what is S of 1? What is the position at time 1? Right. This is the distance moved in 1 second. S of 1 minus S of 0. But since we're just setting S of 0 equal to 0, really if we find S of 1, then that gives us the distance moved in that second. And we'll approximate that using a Taylor polynomial. Okay, so we know that the speed, v of t, is s prime of t, and the acceleration is v prime of t, or s double prime of t. The secondary Taylor polynomial was going to be, well, position, s at 0, and center equals 0. So I suppose we could also call this a Maclaurin polynomial if we wanted to. It's going to be our constant, s of 0, plus s prime of 0 times t to the first, plus s double prime of 0 over 2, don't forget the over 2, easy to forget that, times t squared. But I realized that this is just t2 of t equals, well, s of 0 is just 0. S prime of 0, well, that's just v at 0. Oh, no over 2 there, not yet. That's just v of 0 times t. And s double prime of 0 is just the acceleration at times 0 over 2 times t squared. Or we see that the second degree Taylor polynomial is, well, 0 plus what's v at 0? The initial speed at time 0 is 20 meters per second. 20t. Note that this is in meters per second times seconds, so that's in meters, and that's our distance, which is what we're looking for. The units work out nicely. And then I have a of 0 over 2, that's 4 over 2, or 2, t squared. And that's in meters per second squared times second squared. Again, the units work out to be meters. So when we have situations like this, it's nice to check the units and make sure that we've got all of the moving parts kind of in the right place. But everything does look good. This second degree Taylor polynomial is our approximation for S of t near t equals 0. So then what's S of 1? 1 second later is approximately t2 of 1, which is 20 times 1 plus 2 times 1 squared. That was the 4/2. Or it is 22. So what is the distance moved in 1 second approximately? About 22 meters. Now the follow-up question, can I just do this for any input that I want? Can I just figure out what is S of 60 and go from there? Probably not, right? Near t equals 0. I mean, I suppose we could do Taylor's theorem with remainder, figure out what the upper bound on the remainder is, um, go through all of those details. But I think we can kind of see that, well, if I'm accelerating at 4 meters per second squared right now at time 0, can I reasonably keep that up in a car? Well, that if I kept that up, then over 60 seconds, each second I gained 4 meters per second. Over 60 seconds, I would have gained 240 meters per second. Added onto my 20, I'd be going 260 meters per second. So 260 meters per second, I mean, put that into perspective, that's like 2.5 football fields in 1 second. I don't think any car is going to go that fast. So can we reasonably kind of keep accelerating at 4 meters per second squared for a whole minute? Well, no. So just kind of plausibly speaking, we don't even have to really run the numbers. Is this going to be approximately T2 of 60? No, it's not. That's going to be too far away. That's going too far away from the center of 0 for us to be really confident in that result. But if we're over 1 second, going from 20 meters per second to say maybe 24 meters per second, yeah, I mean that's a fair speed for a car to go. Okay, any questions on series, Taylor polynomials, Maclaurin polynomials, any of that? Let me stop the recording.